All right. So polymorphism is something that we see in object-oriented languages. Polymorphism is simply the idea that you can have many different objects of the same type that have different behaviors. In object-oriented languages like Java, we typically think of two children classes inheriting some sort of a parent class. So you may have an array of the parent class, and it may actually be different children that have different behaviors, and you kind of treat them all as the parent. That is the notion of polymorphism. And the question is, how do you do it in C? And I think it's interesting to talk about how to do it in C because it gives you a significant insight into how it's actually implemented in Java and in other languages. A lot of the usefulness of a class like operating systems, it's not necessarily because everybody's going to go on and implement operating systems, of course. It's mainly so that you can start to see how everything is put together in a system so that you can understand how it works. So one of the reasons that we use C is because it doesn't really hide anything, right? Every line that you write generates code, and there aren't many things that it does magically behind the scenes. So it's nice to investigate polymorphism in that context because you kind of have to implement it all. So we saw last time that C can support generic data structures by using function pointers that you pass into kind of generic data structures. Now we're going to see how we can support polymorphism within C. So instead of the function pointers we talked about last week, we're going to talk about what essentially amounts to structs of function pointers to get polymorphic behavior. It's a little weird, so we'll dive into it. I also said that one of the ways in C is that you get kind of specialized behavior for different data structures, especially when you want the highest performance, is with macros. I'm not going to talk about that in this class simply because it gets real ugly real quick, and it's just more, I don't know, advanced and maybe not as useful for the scope of this class. So structs of function pointers, what does this look like? I want to actually motivate this with a few different examples, and I'm going to start out by by going through a very small little piece of C code that is meant to solve kind of a generic problem in C. And the idea is that we want to have an array of things. Things I chose to kind of be hopelessly generic and meant to indicate that, yeah, we want to be holding generic things, but some of those things are going to behave different than other things. So if we look at what things look like, we simply have the structure definition here. It's basically just a data structure that contains an array of void stars, right? So we've seen this before. When you want a generic data structure in C and you want it to point to a struct of a generic type, great, you use void stars. And here we're just keeping things simple by making an array of those things. And then what we want is we want to have a function that can go through and print each of the items. And a question that we've revisited multiple times in the class is the notion that if we want to print out the items within a generic data structure, and this our kind of struct of things, that's kind of a difficult thing to do, because really we're forced to kind of do what we're doing here. We just iterate through all of the things, and when we find a thing, here we just kind of print out the void star, right? So if you remember the compare function from homework 1, we were kind of put into this bin where it's like, well, okay, if we want to if we want to see if the data structure contains something, then we're just comparing pointers, and that really kind of seemed dumb, and in fact it kind of was. But that's what we're left with, kind of without adding more intelligence. So that's what we have here, just a generic print function for a generic data structure. Now, what are we putting in things? So first we're just initializing it to null, nothing very interesting. And I'm going to create two different types of things here. One, a Fibonacci thing, and that Fibonacci thing is intended to kind of require you to generate the Fibonacci sequence for it, or to print out the Fibonacci number of f. And the second one is a struct for me, for struct parmer, and it has a saying and how many times I repeat it. If you haven't noticed, I repeat things a lot in class, and I'm sure it will get a little tedious. And then I want, just a set of sayings that I can use to populate my struct. So, I have my saying that we've talked about many times already, that the operating system is the good stuff in the sandwich, right? Stuff in the center, most of which I can't eat, but I can't eat the bread either, so, Really, I just hate sandwiches, but okay, it's an analogy, who cares? Second thing, I'll always ask you what's better, right? One of my second sayings. Third thing, obviously when I ask you which is better, it's always a trap, because the fourth thing that I say is that everything in system is trade-offs, right? So here are just a few of my sayings. We're going to populate my struct with a few of those sayings. Now, if we treat these as the things that we're putting into this generic data structure of things, then we'd really kind of want to print out not pointers to these things. Sorry. But instead here we might want to print out the F Fibonacci number. And here we might want to print out the saying a number of times that I'd actually repeat it, right? So this is generically what you want to do, right? So all that we're doing here, I'm not going to go through this code, it's just kind of the dumb thing that you'd have to do if you want to allocate a whole bunch of different things and then populate the generic data structure of things with those items that we allocated. So we're first, every other item within our generic data structure is a Fibonacci, and every other one after that is me saying something n times, or I times in this case. Then we're just populating the generic data structure and printing out all of the values. And we've seen what that looks like and how absolutely unsatisfying it is. If we just run our program, we see, yay, it prints out a whole bunch of different addresses of those things that we mallocked. Like, that is just so ridiculously uninspiring and uninteresting, right? If I were to write a print function, I would hope it would be able to print out something corresponding to the things themselves, right? So, kind of annoying and weird way to do that might be to give each thing some sort of an identifying marker. So maybe a Fibonacci has an integer that identifies it as a Fibonacci thing, and a parmer has a number that identifies it as a parmer thing. The way that we typically think about this is with an enumerated type, and within my enumerated type I might include a thing that is a Fibonacci type, and I might include a thing that is a parmer. Nope, that is not how you spell my name. A parmer type. So now we have two different, what an enum is essentially a wrapper around integers. This will end up being integer 0, this will end up being integer 1. So these are just two integers that might identify which of the things we have. But where do I put that enum? Maybe I do this, and then I have my enum. I guess I need to give it a type. So I use type defs a lot for enums because I think it gives the enum a name, which is good. So this is a thing type, and it is a type of that. So I'm gonna say, well, I could put my thing here, and that's the type of it, and here I'm going to assume that a Fibonacci is always a thing fib. Of course, I can't write that here because, this is a definition of the struct, not an actual instance of it. So maybe I do that, but then, how do I know where that is? Because all that I have is a void star to the Fibonacci. It's not actually clear where this is, or am I just going to have these types at the top of all of these things? And the answer is that yes. When you do object-oriented programming, you typically have these types at kind of the top of the data structure. There is a way that you invert kind of the structure of a lot of lists, but no, I'm not going to go into it. What is very common is, well, actually, I'll leave it at list for now. So now, no matter which void star I have, so long as it's to a Fibonacci or to a parmer, I know that the first thing within that structure is a thing type. So what I'm going to do is I'm just going to create a struct for this. So I'm going to create a struct, and this is a generic thing to start out, okay? Do I have that? No, I don't. Great. And actually what that is going to include is just this type saying which of the types of things it is. And then I'm actually going to put that struct at the top here. And I'll just keep it called, actually, I'll keep it generic. And I'm going to do the same thing here. So now both of my structs of generic things contain a struct as their first item that denotes what type of thing is. And hint, it's also going to include the properties that we want each of those things to have. So now we know at the top of each of these void stars, they have this thing. So what I can actually do, well, first let's populate those things. Let's start with a simple thing, right? So I have my Fibonacci here. I'm going to populate the thing. And I have within that thing, what did I call it? A type. Oops, go down please. Thing.type equals thing underscore fib. So I know I have a Fibonacci. So I know that the type of this thing is Fibonacci. So I'm just going to annotate it as such. Now, the Parmer struct, I know that I also have my thing, and I know that it has a type, and I want to set that to thing underscore Parmer. I actually don't know if this syntax is going to work. It might kind of, actually, I don't think it will work. Let's see what the compiler error is. I'm actually just curious. So let's see what happens here. I missed a semicolon somewhere. So note, it says line 51, so Alt-G, 51, take me to line 51. Cool, I didn't put a semicolon at the end there. Yes, I'm dumb. No matter how long you write C, sometimes you still make dumb errors. So nothing changed because I haven't actually changed what gets printed out. Ooh, lost 2 viewers. Hopefully I'm not saying anything that's too confusing as of now. If I am, please feel free to just tell me to slow down or something. Okay. I've now made all of the things that I want to put into my generic data structure have this thing at the top. And I've added a type that denotes which one of the types of things I have, a Parmer or a fib, right? So now, when I'm printing out the things, I can actually do something a little bit smarter. So let's make a struct thing pointer here. I'm going to call that my actual pointer to the thing that I'm going to find. And now, instead of just, actually, you know what? I can keep things simple here. Struct thing equals that. Know what I've done here? This is a little weird. The type of all the things, if you recall, is a generic data structure. And it's a generic data structure with just an array that holds a whole bunch of void stars, in this case 32 void stars. So now what I'm doing is saying I want to take the void star in TS and set thing, which is of type thing, to it. I know none of the things that I'm putting into this generic data structure actually are struct thing, but I do know that struct thing is at the top of all of the types that I'm putting into it. So it's actually legal to say, I know that no matter which void star I have, I either have a thing at the top of Fibonacci or a thing at the top of Parmer. The thing struct has the same form either way, so this actually ends up, oddly, being legal. So now, instead of only pointing out the pointers, I can say I have a pointer of type D, right? And I'm just going to print out my thing type, I believe it's called type, as just an integer. So that should be 0 or 1 depending on whether it's Fibonacci or Palmer. So let's compile, and it hates me for something. Dereferencing pointer of an incomplete type struct thing. Interesting. Yes, that is true. It is incomplete type because I defined struct thing within my main. But now I'm using it somewhere else, so I need it in the global scope. So it makes sense that it would be with the generic data structure because I am kind of defining all of this together. Indent region. Okay. So now I have my struct thing in global scope. So this notion that it doesn't know what it is hopefully goes away. It does. And now if I run it, I can see that it goes back and forth between Fibonacci type and Palmer type. Fibonacci, Palmer, etc., etc. Okay, good question. Why integer? Enums are integers. Enums are a nice, I don't know, syntactic sugar, just kind of a nice way of referencing and giving names to specific integers. So having this code right here enables me to give a type and nice names to what is essentially just 0 and 1. So it's nicer to use kind of names for things than just constants 0 and 1 because it's self-documenting. People will understand what those names and values are rather than just 0 and 1, which they will never understand. Okay, so we've done something interesting here. We've said all of the things that are going to be stored in this data structure have the structure such that they have this thing struct at the top of them. So now I can identify which of those types of things I have within this data structure. So one thing that I could do is I could say, I could do a switch on thing type, and I can say, I know that thing type is either a thing fib, in which case I'll do some stuff, oops, or it is a, oops, just messed up all the indentation there, a thing Palmer, in which case I can do some other stuff, right? So one way that you can get some degree of variant behavior is to add this type of code. And for instance, here I could say, well, now I know that my, oops, why is that not, I think I messed up my indentation settings somewhere. Oh well, I'll live with this. So now I can say, you know, if the thing that I have is a fib, then I can take my struct fib and say that I have this f and set that equal to thing. Struct fib thing. Now this is not going to work for the previous reason that thing didn't work, but let's dive into this a little bit. So this is saying that I know that the first part of the Fibonacci struct is a thing struct, and that's why I can access its type this way. But once I know that the type is that of fib, then I know that the struct itself is of struct fib. So I should be able to now cast the fib back to a thing, right? So this is how I kind of recover that notion of, oh, I actually have a struct. I should make it Fibonacci, not fib. So I'm going to make the change here. I'm going to go back and just kind of make it so that I can compile all of this. Let's do proper indentation and struct fib, struct Fibonacci instead. Yep. Okay. Let's just see if I can print out the f within Fibonacci. Have a fib struct looking for fib of D, right? Okay, so how do I access that? I have my f within there. Let's look at that to verify. Within my struct Fibonacci, I have my Fibonacci that I want to actually access, which is f, right? And now I can access that because I found that I have my struct Fibonacci. Let's see if C yells at me here. Oops, not what I wanted. It does yell at me because I missed that. If you think that after writing a ton of C you get better at those types of errors, yeah, not so much. Interesting. What did I do? Struct thing type. Am I doing something dumb here? Make. Okay, this is not working as I expected because of an error somewhere. My God, you are a hero. I'm not a big fan of the case statement, the struct statement in C. So now you can see this is doing what we want. I can actually print out information about Fibonacci structures within my print statement. However, this is no longer a generic data structure because this printum function, which is supposed to be the generic function for things, not so much. It's no longer generic because now I am hard coding in here all of this information. I'm hard coding whether it is I have parmer structs, I have fib structs, and I would have to add for every single struct a different item within here, a different case within here, right? So that's a huge problem because I no longer really have that generality. Imagine if you were implementing the printum function within a library. Well, the library can't guess every single type of every single user type. So this is one way to get variant behavior, but it's not really the way to get generic data structures. This is how you see a lot of functional programming languages do a lot of this using match statements. This is how you do it in C. So let's back up. If we don't want to have this because this case statement will just kind of blow up and kind of be everywhere, right? We'd have to have a case statement for everything. This is not great because it requires, that the generic data structure know of each possible type of thing we can hold, i.e., clients can't define their own. So that's a big problem. Let's see if we can actually fix that a little bit. Never a good idea to hard code if you don't have to, right? Love the enthusiasm there, absolutely. So let's see, let's actually truly make this general. To make it general, we have to go back to this concept of the structure that now every single thing has at the top of it. Our Fibonacci's have thing at the top. Our Parmer has thing at the top. What we have to do is combine what we learned last time about function pointers with what we've now learned this time about having kind of this ability to have struct layouts be very well defined in C. We now have things at the top of all of our different types. So what we want to now add is a function pointer within here for printing. So I'm going to make this return void because it's printing. It's a function pointer, and this is how we do syntax for that. This is my print function that every type is going to have to define on their own. and it's going to take a pointer to a void star, which is the actual value itself that it's going to print. So it's actually kind of passed a pointer to itself. So I'm gonna make a note about that because that's weird. First, I'm gonna say this, because in Java that's essentially what it is. The pointer passed to the print function is essentially this or self, depending on which language you're using. Okay, so yeah, what does this look like? So now I know that I have my thing associated with Fibonacci. Let's write a print statement for Fibonacci. I have written the Fibonacci sequence here. I haven't tested it, so, you know, let's hope it works. So I have my Fibonacci here. My print statement, I know that it has to have this, I know that it has to have this shape. So it has to, it has to take a void. I'm going to call this my fib print function, and it has to take a void to what is essentially us. And all that we're going to do is say, you know what, actually, I know that what is passed in is a Fibonacci because that's how this works. So I'm going to say that I have my struct Fibonacci here, and I'm going to say that's actually what this is. I know that it is because that's how we're orchestrating it. So now I know that I have my Fibonacci, and I can now call printf and print out exactly what I want to print out. So the Fibonacci of the value stored here is some value, right? So f, that's the Fibonacci that we're supposed to compute, and I'm going to compute that by f, right? Remember, f is the integer for the Fibonacci sequence there, right? Okay, I'm going to now do the same thing for Parmer. So I'm gonna just kind of copy this. Copy and pasting bad, folks. Don't do this. But, you know, I'm gonna replace everything. So what can you do? So I'm now, if this is called on the Parmer struct, if this function pointer is called on the pointer struct, then I know that I have a struct Parmer. So now, how do I print lists out? Well, this is a little more involved. If you remember, I'm going to be repeating things a number of times. So, you know, I need to have some sort of a repeating facility, otherwise known as a for loop. So I equals 0 while I is less than gp rinse, spelling correctly, rinse and repeat. How many times do we do it? I plus plus. And then let's do a printf of whatever I am supposed to say, and say it that many times. You know what, let's actually say it noisily all on the same line so that I'm actually really yelling and saying it really, really quickly because, you know, that's what I do. And then here, obviously, we don't have a Fibonacci anymore, so let's not do any of that, but I do want a print line after I, you know, say my stuff. So now we have a print function specialized for each of the this types that we have, right? So now we have to use those. We have to set those up somewhere. Someone's asking if we have this int type for each of the things. We do still have this int type, but we're actually not going to be using it anymore. So we're actually, I showed you one way that we can do kind of the variant data structure generally. Now I'm telling you the other way. So this actually, it is very common in object-oriented programming languages, but it's not necessarily going to be required here. So we're kind of moving on from that int and really just focusing on this function pointer associated with a generic thing, right? Okay, so let's go back to our printum function, right? So we don't want to do all this crap printing anymore. So let's actually just make this, let's yell at lists sufficiently. Not generic, go away, get off my lawn. All right. So now we know we have a thing. We also now know that all of our things have a function inside of them. So let's actually just call that function. So we know that all of our things have a function called print function. So let's look at that. Print function. And what does print function take? A pointer to ourself, which is essentially thing. It takes a void star. Let's see if this works. Now, the only problem is that we haven't actually set up these print functions yet, so we need to do that. We need to actually say, well, okay, if we are a Fibonacci type, then our thing.print function is a fib print function, okay? And let's make this look nice, because code craftsmanship is important, and making our code readable makes it both easier for us to debug it, read it, and for future people to read it, debug it, and use it. Not that I have strong opinions about this or anything. So I have barber print, is that what I called it? Yes, sure is. Awesome. Print function equals, and make it pretty, because making it pretty doesn't take much time, but makes it a lot more readable. C and ID, yep. Okay. Holy hot. We have something weird going on here. We have something interesting in that, ooh, the Fibonacci is actually working out wonderfully. Fibonacci of 0 is 1. Fibonacci of 2 is 1. That's true. Fibonacci of 4 is not 3. I don't believe. So fib of 2 would be 2. Fib of 3 would be more than that. So I don't believe that this is actually right? So, okay, maybe the way that I'm doing Fibonacci, maybe a little off. But I'm getting something weird going on here. That here I'm supposed to get output for myself. Is a trap, it's a trap. Is, you know, actually printing out correctly. But then I have some weird stuff going on here. So I don't know what that is. Let's kind of check out what's happening here, right? So my print function is getting set up correctly. My words are getting set up to be, oh, okay, well, yeah, that's not going to work. So I just have a logic error because dumb. How do I want to do this? Let's just try that. This might blow up in my face. And let's try this as well to just more easily debug this. I'm not going to go over the logic behind this because who cares? It's not the point of this. So this is just normal debugging stuff. So we can start to see that things are starting to make sense. The first one is not printing out at all, and that's because rinse repeat is probably set to 0, so let's fix that. Point being, hey, look, I now am iterating in a generic way through a C data structure where my library did not need to have any specific logic for the client's type of object. All that it had to do was say that the things that this data structure support are struct things. And everything of that struct type has this function defined within it. And you as a client, you need to define those on your own. Once you define those, then you're good to go. You're off to the races. I will be able to call it on your objects when it's appropriate for printing them. So this is really cool. This allows us to define generic data structures in a way that is immensely powerful. So you can see this is working. We have two things of very different types, Fibonacci's, and me yelling as I do in class. So that's what this is. It's nice to see that, and it's nice to see how it's done, but I want to take it a step further. This will not take very long. I actually don't think that we're going to go as long as we have today, as we have historically today, hopefully. I want to show you what is essentially the Linux, or really most kind of Unix systems, a representation of their data structures behind the hood. And I want to motivate why what we just looked at, where we have these generic types with structs that contain a whole bunch of function pointers, is really a useful thing that you see in real systems. So what we see here at the very top are your applications. I'm actually going to go over an example of where we'd have these generic data structures. In class, we've seen a generic data structure, which is just a priority queue, which you might want to sort by a metric defined by the actual applications themselves. But let me go into this example. So in this example, we have all of our applications, all of your processes that are executing in your normal user level things. They make system calls like read, write, open, stat, etc. Read and write are actually system calls that are performed on terminals. When you write to a terminal, you output to the screen. When you read from the terminal, you read user input. They're defined on files. So reading from a file, you get the contents of the file. Writing to a file, you write to the file. They're defined on sockets, which are used for network communication. When you read from a socket, you pull data in off the network. When you write to a socket, you send it out to the network. As you see, we have these read and write functions that seem very similar to our print function. Somehow, we're treating this one read call in a very generic polymorphic way, depending on what the backing actual object is. So in operating systems, we have these generic data structures and generic properties because we have this API that is generic across many different types of objects within the operating system, right? So here we have what's called the virtual file system, or the VFS layer. The VFS layer's job is to make it so that these generic read and write calls to kind of our generic data structure of something that we can read and write to go to file systems, to the network, to some sort of a weird fake file system like the proc file system we saw earlier in the class, special purpose file systems, etc., based on the type of the thing that you've opened, right? So this is really cool. And this is actually how you do it in operating systems. So let's look at that. We do this class, of course, in XV6. And you all, at this point, oops, yeah, I am in the wrong window, even though I've changed Twitch. This is XV6. You guys have all looked into XV6, the operating system, a little bit. And if I wanted to, I looked at that diagram that I just had up, and I say, whoa, this idea of a VFS is really cool. And I know XV6 allows me to read and write from pipes. It allows me to read and write from terminals. It allows me to read and write from files. It must have this type of code in it as well. So I kind of start looking through the code, and I see that within this, I just start looking randomly around, right? And I think maybe files have this type of code. So I go into file.c, right? And you can see that, well, in this case, maybe I kind of find this file read function. It looks like I'm doing read on a file. So that's cool. All right. And here we actually see exactly what I was talking about. Here we have files that are passed in. This is kind of a generic data structure, and it has a type associated with it. So if we actually look at the type of file struct, I see that enum that we saw before, and you can see there's either it's not a file descriptor, it doesn't really have anything useful, it's a pipe, it's a pipe, so it contains that type of a data, or it's an inode, and you know, we'll get to that much later in the class, but that's basically a file, okay? So this is really cool. I can tell what type it is based on this. Now, XV6 is very simple, so it doesn't kind of use different structs, one for the inodes, one for the pipes. Instead, it has within this generic file struct a separate pointer to the pipe, if it's a pipe, and a separate pointer to the inode, if it's an inode. This is another way to do it. It's a little, has more overhead, but it's easier to understand. So, you know, that's why you actually have this type of thing happening. That's why you have this kind of different structure. So you actually see that first type of kind of variant behavior here. You see that we have different types, and if it's a pipe, then it's going to call the pipe read function. And pipe read, you can imagine, yeah, it's doing all of the pipe stuff, right? Okay, we certainly aren't going to go into that here, but sure. If it's an inode, i.e. a file, then it calls the readi function, right? And readi, well, let's just assume that it's something for a file. You know, maybe I want to just confirm how I got here. I want to make sure that this is the system call. So in my editor, what I can do is click on a definition of something and it'll take me to the places that it's invoked. In this case, it's really only kind of invoked in two places, one where it is defined and then the other in this location. So it took me here. This is, I just really want to emphasize, as I pointed out in a previous class, that you really want this functionality to jump to where functions are called. So anyway, back to what I was saying. This file read function, I think that's what's called when I make a system call for read, but I really want to make sure, right? So yeah, actually, as it turns out, it's invoked by sysread, and if I've read the XV6 documentation, the documentation for XV6 says that all of the sys underscore functions are the actual system call bodies for the corresponding system calls. So this is the system call body for the read system call, right? And to help a little bit, you can see it's in the sys file. Okay, yeah, that looks like system calls to me. Okay, so let's go back to where I was. I'm on the right track. So let's go to the definition of read file. Now I know, cool, XV6 is using that kind of parametric method of saying, like, if it's this type, do this thing, otherwise do this other thing. I use the switch statement in my code, that's fine. They're using conditionals, that's fine. But I want to point out something else. And that's that this is still referring to inodes here. Read I, hint, the I stands for inode. So why is it not just talking about files? Let's go in here. So in readi, it is talking about something a little bit more generic. Where did you see panic? Somebody's asking where... Oh, panic. Yeah, okay, here. Panic just causes the machine to shut down. You know, says it's basically an assertion for the kernel. Don't get there. It'll bomb out. So this is essentially assuming that either the type is pipe or inode. If it's anything else, it's going to bomb out. Again, assertions are good, folks. Do them. Write your code defensively. It'll help you debug. So readi, we're reading an inode. This is in fs.c, filesystem.c, so I think we're on the right track. That indicates to me that maybe this is a file system, but I know that we are getting passed in an inode. So something's going on here where maybe it's not just files, maybe it's something else, right? So here's where we kind of get to the crux of it. There are a number of devices within XV6 and within Unix as well. And there are very commonly files in your file system that are not files as we think about them. They aren't things that you store data in and you can get out of them later. and get that data out of them later. Devices are the physical devices on your system. So for instance, there is a file within Linux for pretty much all of your actual devices. So within the dev directory, here literally are files that represent my real devices on the system. So if I were to, for instance, cat SDA1, that would probably start just spitting out the whole contents of the first partition of my hard drive, which I'm not going to do. So, wow, there are these files that are actually devices. So here's where you start to see kind of another use of that type thing. Oh, okay, here we see it's a device. But devices, every single device, because we're talking about the peripherals here. When I read or write to a hard drive, it's going to look very different than when I read or write to a networking card, right? Or to a terminal device. So now we reach the second form of polymorphism. Here we have a device, a dev SW array, and I actually, to tell you the truth, don't know what SW means. But I do know that the struct dev SW means, or not means, it is all of the devices have this struct, they define it, and that struct includes two function pointers, one to read and one to write. Now we're starting to see where kind of that generic print function, one that we defined for Parmer and one that we defined for fib, is starting to come into play. Because yes, now we kind of have the same thing, but for these read and write things. Let's see where the dev SW is actually defined. I can see it's defined there. I want to go here. So in console.c, I can see that dev SW, one of these device entries within the array of devices is a console. Again, this is an enum somewhere, but it sure makes a lot more sense to read code where it says console there instead of 0 or 1. Enums are just documented code, right? And here we're saying, well, I want to create this device. Right now we're initializing the console, if you can't tell from the name. So we're saying, yeah, I want to initialize my console device, and how I'm going to do that is by adding the console entry to this array of devices. And I'm going to add my write function, and that's going to know how to do console write stuff. And my read function, which knows how to do console read stuff. So if you look at the body of console write, it's doing weird stuff where it's basically calling console put C, which gets a little gnarly. I'm not going to go into lat code. So this is actually writing out to the console. So we are here setting up so that when the generic write function is called on a specific device, it will resolve to, in this case, the write for the console. So going back to where I was before, we can see that when we call read here, if this device that we're operating on is a console, it will call the console read method. However, if it is in, let's say, like a hard disk, well, it's going to call a different read for the hard disk. Let me just scroll down. What do you want to see below here? Probably talking about the previous screen. Yeah, I don't know where you're talking about. Okay. So hopefully that makes sense. All that I really want you to understand here, one, I want you to see what it's like, how you should be able to browse around XV6 from your editor. It should be relatively easy to kind of dive around a lot of the XV6 stuff because it takes practice and you need to kind of get used to it, but once you get used to it, then you get a lot more productive being able to jump around the code effectively. So So I think this is maybe what you were referring to that you wanted me to show. Anyway, so long story short, I just want to harken back to our initial stuff, right? We have a generic function, printum, and here we have a struct of things. And all that we're doing, instead of adding specialized code for printing out the different things, we're just calling a function pointer for that thing. We're doing the same thing in real operating systems. In xv6, it's pretty simple. We just define read and write. In Linux, there are probably 20 functions that define the things that you can do on a file. But the concept is exactly the same, right? I want to go one step further, and I'm not going to go into many details here, but I want to give you an example of how you actually can do fairly generic object-oriented programming in C. And I'm not going to go into a lot of detail here because a long time ago I created a repository called C Object Models Instructional. I think this was for a workshop for ACM in like 2013. Yeah, February 2012 was my last commit. This is a whole bunch of code that actually just implements different forms of object orientation in C. It's ugly, so you would never actually do this. Oh, well, there are systems that do, but they're ugly. So this is much more pedagogical. Once you understand how this code works, you actually start to understand how real object orientation works. So the idea here is that I provide two implementations of object orientation. One is a Java-like model of object orientation where you use single inheritance. So you can have children that inherit from parents, parents from provide functionality to children, etc. And you can dispatch to parent functions using super, etc. And it supports proper polymorphism, which is kind of what we've been talking about. The second version is actually really interesting because it implements prototype version, a prototype-based object model. And this is actually what backs JavaScript and a lot of dynamic languages like Python. And it's actually based on a much more dynamic version of object orientation around duck typing. So this is just an implementation of both of them that you can use to understand how you'd actually implement object orientation in both of these languages. I can go through these if we want in a later version of these office hours, but it would take much more time than we have now. So at this point, I just want to point out that this repo exists, and you can find it in my account. It's public, so please feel free to go there. I also seeded all of these with a set of advanced questions. If you go deep enough, you might be able to answer them. So that's kind of all that I wanted to talk about. Let me answer some of the pending questions. So you're confused on what happens when you're writing an integer versus a char. You mean to the console? Into the struct, into the console. Yes. Okay. So let's look at that. I mean, the prototype for read and write, it says that you only read and write characters. So that's it, right? You don't really get an option to write a char. If you want to write a char, you're gonna, basically be writing 4 characters or something. So the API for this is really just that you're writing characters. So if you look at the destination is really a char star. So the only thing that you actually read and write from the read and write APIs is arrays of characters. That's it. So okay, if that's all of the questions about what we were talking about here, I'm going to, stop recording. Oh, so what if you want to write an integer without touching the code? That is not generality within the types of things within the data structure. That's generality within the types of arguments that you pass to the data structure. Method overloading is the way that you typically do that in Java. In C, you honestly just define a second function that instead takes the argument of a int. So that's not interesting in C. A lot of it is manual or done with macros. So anyway, we can talk about that one later. Making this be able to work for a char star and int star, you would just have read I and read I underscore int or something. It would be two separate functions. To confirm my understanding, the ability to cast to a void star to multiple things is possible because we have concentric structs that start at the same memory address. Yes, correct. C makes guarantees about struct layout that allow you to do that. A lot of languages make no such guarantees about struct layout, so you cannot do that. Okay, now you're at, no, that's a different question. So when we do our print function, okay, so the question is, wait. So if you're printing like an int versus a char star, no. So the difference here is our print function doesn't take an int, it doesn't take a char star, it takes a thing. And if a thing contains chars, it will print them as chars. If the thing contains ints, it will print them as ints, simply because we have our specialized print functions that know how to either print it as a string or print it as an int, right? Okay. Okay, so let me